So today will be our second lecture about virtual memory. And I think the most interesting thing is for some of you might end up in your lives implementing a lot of operating systems code and doing that kind of work, for which this will become a fairly large focus of that effort. For the rest of us who are more application programmers, though, what you'll find is if you just kind of have some general idea of what the operating system is doing and some of the ways you can kind of tweak what's going on to your advantage, that's the benefit of knowing this kind of material. So you'll recall from last time that the idea of virtual memory is to provide an indirect connection from the memory that the programmer sees, just think of it as an array of bytes, and the actual physical DRAM that's available to use to hold that information. And so in general, that's represented by some type of a page table, which consists of page table entries, and each page table entry describes for a particular block of memory, a page, where it's located. Is it in physical memory, and if so, what's the starting address? If not, is it on the disk? So this page table will have various flags, one of which, a simple flag, is just, is this particular page valid or not? Meaning, is it in the physical memory? And in general, this all works partly by we're partitioning our whole memory space, both the physical and the virtual, into these uniform size blocks or pages. And we also talked very briefly that if you work out the numbers, when you get to a moderately large address space, you can't possibly have page tables to represent your entire allocated virtual memory. So what's typically done is a tree structure implemented by a hierarchy of, or levels of page tables, where you can think of it as a tree with a branching factor equal to the number of page table entries per page. And so at the top level is a single table giving sort of one page's worth of page table entries, but instead of pointing directly to the memory of the user program, it's actually then pointing to additional set of page tables. And then this keeps going, possibly multiple levels. And part of the trick here is that except for rare exceptions, most users have only a very sparse utilization of their total address space, that they're using the region at the top for the stack, they're using the region at the bottom for their code and for their global data structures. Malloc is allocating typically from the bottom, but if you work out the numbers, if like the machines we have with a 2 to the 48th bytes worth of virtual memory, we're actually typically using a very small fraction of that. So the interesting thing about this tree is you only have to populate those parts of the tree for which there's actual pages in the program to represent. So this tree can be reasonably compact. It sort of grows, it scales in proportion to the total used virtual memory space as opposed to the size of the virtual memory space. The other thing we talked about last time very briefly was to make this go fast, you'd have to have some type of a caching scheme for page table entries. And otherwise, you'd end up having to go to memory over and over again to walk down this path of page tables. And there was a question last time, it was a really good one, which was, well, assuming a cache is pretty fast, if a typical read takes 2 hits, one to get a page table entry and one to get the block, that doesn't seem so bad. But actually, if you work it out with a multi-level page table, if you didn't have TLBs, you'd have to do K plus 1 memory references just to get 1 byte out of the user's code, memory data, because you'd have to start at the root and chug along. So the idea of a TLB is it's essentially a hardware cache of page table entries. So it has information there about what level in the tree it is, what user process is running it, and but basically each of these entries is just a single page table entry. And assuming there's a hit then, that can very quickly find, and actually all done within hardware, can locate where a given virtual address maps to in physical memory and use that to directly return back the value without any more fooling around with page tables. So you can see that TLB is pretty critical to making this work. By the way, people ask, why is it called a look-aside buffer? And I don't know, this is something from ancient history. Ancient history being the 1960s. So you remember the general principle of set associative caches, that typically there's a, for a given block can map to somewhere within a fairly small set of possible lines in a cache. So if we say it's four-way set associative, for example, then there's only 4 possible places any given block can be. And you'll find that both data caches are set associative, but also TLBs are set associative, typically with higher degrees of associativity. So, and the way, if you remember from your cache simulators, of course, was that the way we figure out where something is in a cache is we get an index from that's the log of the number of sets, and we use that to determine which set to look in, and then we have a tag, which is the rest of the address, and we use that to identify which of these blocks matches the block that we're interested in. So that same principle holds for TLBs as well as for caches, for data caches. So, so far we've introduced all these different symbols and numbers and things. And I'm introducing this because we're going to sort of show some very simple mappings just to exercise to get you from a virtual address to an actual block of data in a data cache. So we say in general that there's capital N bytes in the virtual address space, capital M in the physical address, and we assume that a page table, each page is P, capital P bytes, and then the lowercase letters are the log base 2 of the uppercase letters. And we talk about there being, for virtual addressing, there's a virtual page number, or virtual page offset, which is the lower order byte bits, and the virtual page number, which is the higher order bits. And similarly, since remember that a TLB is a cache of, you see that? I'm pointing to things with my finger and it's not showing up there, is it? Oh, I wonder, what have you been looking at then? Okay, I'll try with this pointer. Apologies to the video people. Technology doesn't always do what you want. So the point is that the TLB, remember, is a cache of page table entries. And so the page table entry, the sort of address, quote, that a TLB is using to determine, to map into a cache is the virtual page number. And just like the set associative caches we've seen, we'll use the lower order bits of that virtual page number to provide an index into the TLB, and then the upper bits will be called the TLB tag. So let's just do some really simple examples of sort of much smaller than real life cases. So let's assume we have a 14-bit address, virtual addresses, and 12-bit physical addresses. and that the page size is 64 bytes. So the offsets then are 6 bits to make up the virtual page offset, because 2 to the 6th is 64. And let's just think about then that the TOB is has 4 sets, and it's a 4-way associative. And so you can think of the TOB then, there's 4 sets, each of which has a tag, and then if it's a valid entry, remember the idea of a TOB is to map virtual page numbers to physical page numbers. If it's invalid, it doesn't matter what the PPN is. So let's just take an address, hex 0D. And so what we'll do is we'll, as the colors indicate, we'll use this low order 2 bits for the index. So the index is 0, 1, meaning that we're in set 1. And the what we'll find then is that the tag is these upper 6 bits. And so one thing you have to do when you do these problems is deal with hex numbers. So you can think of this is a 6 bits total, but when we convert this to hex, we look at the low order 4 bits and say that's a 3, and then the upper 2 is just 0. So you can think about adding 2 extra bits to there to form 2 hex digits. And so our tag is 0, 3. And so that, as this yellow indicates, that's a hit. That we find that tag in the TOB. It says the physical page number is 2D, which is not related to the 0D. That's just a coincidence there, that they're both ended D. And so that would then give us our physical address. Similarly, we could look, if we didn't have a TLB, we could look directly into the page table, and we could look up the the page table entry for virtual page number 0D and find that it's 2D and it's 1. And it's pretty important, in fact, that the TLB entry and the page table entry be consistent with each other, or you've got a problem. So that gives us this overall mapping that our physical page is at 2D, and we didn't worry about the low order 6 bits of the address. They just carry over directly from the virtual page to the physical page. And now if we wanted to just keep this going, we could say, okay, now I've got a physical address, but I want to get see where it's located in the data cache. And let's assume that we had some low order 6 bits for the physical address. Then what we do is, just like you did in your cache lab, you'd say, well, the block size of the cache is 4 bytes, so the low order 2 bits are the block offset. There's there's 8 sets here. No, I'm sorry, there's 16 sets. So there's 4 bits worth of cache index, and the rest of it forms the cache tag. And then we could pick those apart, and again, with some work, find that what we're looking for is byte number 1 with index A here, that's hex A, and with a tag of 2D. And so that keeps going. And there's more examples here. I don't think I'm going to go through them all. Actually, these slides are really interesting. I didn't make them up. Somebody put in a lot of time on them. But one piece of advice, if you want to go through them yourself, make sure you do the PowerPoint version, because there's a lot of animations where there'll be one table that sort of sits on top of some previous thing that was there. But anyways, this is an example of the same kind of parameters, where there's this time the virtual page number is 0f, but we'll do the same, splitting that into a TLB index of 3 and a TLB tag of 3. And so now we look in seems. What happened there? Oh, I see. I was getting confused by this word physical address. That shouldn't really be there right now in this part of the animation. So basically what we want to do is look in set number 3 for tag 3, and we find it here with physical page 0D, and it's valid. And then similarly, we can take the address and put in the physical page number and take that address and use the cache to look up the cache index of 5 and a tag of 0D, and so we find it. This is a direct map cache. And this is an example where the TLB misses, and you have to go then to the page table. But you can see that the virtual page number is 00 here. So you look at the first entry, you find that it's valid, and that gives you the physical page 28. But it's totally possible for the TLB to miss, but the cache to hit. So that's a possibility, and that shows in this example too. I don't remember how, in this case it's a miss, but it could have been a hit. So just to give you, to scare you a little bit, this is an example of an exam question from several years ago, back when we had used printed exams. For somebody writing this exam problem, was a little bit funny, saying that assume the system has one or more boats. So whoever made up this slide thought that was pretty funny. But the problem's actually a really good one, in that what it gives is a list of, this is the information of what the TLB has, the TLB contents, and then there's a series of questions where you're given either a virtual address and you're supposed to give the physical address, or the physical address and you're supposed to give the virtual address, which is sort of involves using this table to work your way backward to a virtual page number. So it's an interesting problem. And if we do this, you often have to be handy in hex. But it's the same idea as before, that we said there's the page size in this case is 2 to the 8th bytes, so the low order 8 bits are the offset. The virtual memory is 2 to the 16th. So there's, and it's a two-way set associative with 8 entries. That means there's 4 sets with 2 elements each, and that's what's given here. So it means our TLB index will again be 2 bits, and the TLB tag will be the remaining 6 bits. And so again, we take this address 785. You'd have to write it all out in binary, which is actually bad notation here. It should be 0B. and then you split that into these different pieces, and you know already what the low order 8 bits are going to be. But then you use the index of 1, 0, or 2, and a tag of 1F, and you find this entry here, and that will correspond to physical page 9F. And so that gives you your physical address. And you can work your way through, as these dashes show. Some of these will turn out to be ones where there's no valid translation. The address is not mapped, at least via the TLB. But you can, in this one example, go from a physical address back to a virtual address. So, of course, the biggest mistake people make is screwing up the hex stuff and messing up where those bit fields are and things like that. And once you're off on that, you're completely sunk. My advice is practice before the final. Okay, so that just shows you, sort of, gives you this sort of very hands-on feel for how virtual addressing works. Now let's look at a real system, and while we're at it, let's look at a system that we know and love, which are sort of modern x86 processors when running 64-bit mode. So there's a lot of caches and TLBs in a modern processor. So, for example, the system has 3 levels of cache, and at the level 1, there's actually 2 separate caches, one to hold instructions and one to hold data. And the reason for that is you want the instruction reading to not kind of get mixed up cache-wise with the data. And having a fast instruction cache is incredibly important to be able to, for the machine to kind of keep reading down filling up the pipeline of instructions and keeping the whole system running fast. So that's part of the reason why it's separated from the data cache. And then there's a L2 cache where these two are combined. And then there's also an L3 cache. And one thing we'll see as we get into later in the term is what's called a multi-core processor. There's actually multiple CPUs. So like most of your laptops probably have 2 or 4 cores. This phone has several cores, I think 4, plus several graphic processing units. So the point is that these cores, each of them has some private cache, the L1 and L2s, but the L3 is shared by all the different cores. And that's useful if you have a program running where, because the scheduler makes it hop from one core to another, it doesn't lose all the cache contents as it hops, gets scheduled on a different core, because the L3 core can still do it. And then over on the address translation side, you'll see there's actually 2 levels of TLB with a separate TLB for instruction and data, just like there were, I'm sorry, for the instruction and data, just like there were for the caches themselves. And there's a larger TLB that holds more of them. So one thing you'll notice about TLBs is they're pretty small, right? 128, 64, 512 entries. So when you think about their job is to cache page table entries, somehow 512 doesn't seem like that many, but that's enough performance-wise, and part of it is by making these memories very small, they can make them very fast. And then there's more stuff. This is the DDR3 is the type of DRAM that's installed, and then this quick path is the communication mechanism between the different cores. So one of the odd things they do is, so that's a way that the cores can interact with the DRAM. But what's important for us is all this stuff, the cache, mostly the TLBs today. So this is how the addressing works in it. And these numbers all kind of fit together. You'll see that, remember that a virtual address is only 48 bits in a current x86, even though pointers, they've allocated 64 bits for them. The reality is that the biggest systems you can buy today still only are limited to a 48-bit address space. Only, remember, 48 bits is 256 terabytes, so it's a fair amount of memory. So anyways, and the page size is, there's actually several page sizes supported, but in Linux they just use a 4096 byte page size. It's pretty standard. So that means that our address can be split with a 12-bit offset and a 36-bit page number. And you think about it, each TLB entry is going to be 8 bytes. And so in a 4096 byte page, I can fit 512 of them. And 512 is 2 to the 9th. So what they do is take this 36-bit field of virtual page number and break it into 4 9-bit chunks. And that becomes how you index into this tree of page tables. So in general, it's always that way, that you look at how big is the page size, that determines this offset. It determines how many entries, page table entries you can fit in a single page, and then that defines how you want to break up the rest of the address into chunks. And then in general, this will go through a TLB if we look at this. Let's see. Trying to figure out where they got 16 sets, 64 entries per set. That would be this is the L1 data TLB. Right, so there's 64 entries total divided into 16 sets. So that means when it's computing the when it's indexing into the TLB, it's using the low order 4 bits to find which set to look at, and the upper 32 bits is a tag. And this shows what the page table entries look like. And these are for the levels 1 through 3, meaning they're page table entries that are pointing to other pages, page tables, not to the actual data itself. And you can see that they actually, one interesting thing is they've allocated 1251, that's 50. That's 48? No. Oh, I'm sorry. This is, yes. So this is, tells you where the actual page is located that it's pointing to in physical memory. And so 51 minus 12 is 39, right? So that many bits. But remember, it's always going to be in a multiple of 4096. So, anyways, there's a lot of bits there for representing that. And then there's all these 1-bit flags. So, and they aren't in a logical order. XD is the extra bit saying whether or not you can execute this, the code in this block. And for this case, when it's in one of these higher level page tables, that means sort of it applies downward over the entire subtree that this block, this page table entry is represented. And it's inverted in its sense, it's a disabled bit. And there's other bits here. We'll look at those bits. They make a little more sense when we look at the bottom level page table entry. So the same idea, the bottommost page table, the one that's pointing to the actual pages of user data, is looks very similar to the upper level ones. It's got this execute disable bit. It has a bit saying whether it's valid or not. That's this p bit. Is it present or not? And then it has permissions. It says, is this a read or write permission for this? And then there's another bit. Remember, we saw this in one of the examples last time where I wasn't sure it was the way it would work. But indeed, what it will say is a given page is either user level or supervisor level. And supervisor level, a supervisor has access to any user level page as well. But it also says what type of, is it read-write, a read-only, or a read-write access to it. The other thing that's interesting is you can even set what the write-back policy is for a given page by twiddling around with its page table entry, which is pretty crazy if you think about the cache having to figure out whether it needs to evict a block and write it back. It has to then find the relevant page table entry for that block, as it doesn't. Or it basically has to store that information away somewhere as part of the block. These things don't implement a true LRU. They implement a sort of pseudo LRU that the hardware provides just a 1-bit flag saying, has this block been accessed since the last time you set this flag to 0? And what the operating system does is it just periodically sweeps through them all and sets them all to 0, with the idea that if it comes back and it's set to 1, it means, well, it's been used fairly recently. So it's sort of like if you think of an LRU where you only get 1 bit of information. The dirty bit is the same idea as in a cache, whether this particular page has been altered. And as I mentioned, this address then is 40 bits, but remember it references, it's basically a, gives the physical page number. So if you add that to 12 bits, you actually have 52 bits worth of physical address, which is strange. So the physical addresses in some ways are bigger than virtual addresses. Does that make sense? And these entries, by the way, this is a place where this is what the Intel hardware supports, but the operating system is really responsible for managing most of this information and doing what it wants to with it. So anyways, what happens is you can think of this tree, this 4 layers, as sort of narrowing down the region where this particular address references in the virtual address space until it comes down to the actual page, and that will give you the physical page number. So like I said, this sums up 40 plus 12 to 52. So one of the things, I sort of alluded to this last time, and it's sketched out here, is this very clever trick of sizing the cache, the data cache, in relation to setting the page size. And that's to let you, the point being that the virtual page offset is 12 bits. But if we look at the cache parameters, we'll see that the cache offset, it's a 64 bytes per block. And the cache index, the way they size the total cache size and make the associativity, it's 6 bits as well. And so that sums up to 12, which is the size of the page offset. And so what that means is that the cache can begin looking, retrieving all the, basically does a parallel read of all the elements of a single set using just the offset from the virtual address. And in parallel, the TLB fires up and tries to find the physical address. And then after that's done, the cache will be able to then say, okay, I've just read, if it's a four-way associative cache, I've just read 4 different possibilities. And now I can, in parallel with the hardware, see, do any of those match my cache tag? So it can basically do the first part of the cache lookup in parallel with the address translation. So now let's talk, that's sort of the underlying hardware operating system stuff. Now let's look a little about how a Linux process manages the virtual address space of a process. And so in general, the virtual address space for a process, we've already seen this lower part where there's some stack, some shared libraries, and then parts of the user code, global data structures, and any allocated memory for malloc. And at any given time, then there's something called the break that controls how much of the address space has been allocated. And when malloc tries to grab more memory, if it's if there isn't enough in the heap yet, it'll make a call on the break to move the break up. And potentially in doing that, the break has to create more new pages and add them to the virtual address. And similarly, the user stack is not very big. It's usually 5 megabytes, but still, as the stack grows downward, the operating system might have to add more pages to the virtual address and physical address of this particular process. Now, up above the addresses that the user level code goes is the information that the operating system maintains on behalf of the user. So this is code that the kernel makes use of, but you as an application programmer aren't allowed to either read or write this data. And so that will include the code of the kernel itself. They actually map the physical memory into this address space, and you'll see that it's done in a way that this is the same for all processes. So this is sort of really a big shared region of memory. And also the things that are specific to the particular process, the various page tables, these various, the stack that the operating system kernel uses, it doesn't run on the regular user stack, and various other structures that kind of keep track of the state of this process. And then overall, then logically, a given address space for at least the user code can be viewed as these contiguous regions with holes in between them. So for here's just showing some part of that. There'll be some range of them that are the text, meaning the code, and these are marked as a special region because it's always read-only. And then there'll be the global data structures that have been allocated in the program. And as I mentioned, any ones that are dynamically allocated by malloc will be a data region. And then there'll be some shared libraries that are actually, you want to share, even within the processor's memory, all the copies of those shared libraries. So the Linux managed all of this as a linked list of what are called VM area structs, virtual memory area structs. So each of these is an area. And each of them is marked then by a starting and an end, some protection information and other types of flags. Flags indicating whether this block is private to this particular process or shared across processes. Protection meaning is it readable, writable, executable. And logically then these are all stored as a linked list. So what the operating system is supposed to do then is if it is given an address, and let's assume it's a miss you know, the TLB miss, so it goes up to the, and then a page miss, so it goes up to the operating system as a page fault. What's it supposed to do? Well, if it's to a region that hasn't been mapped, it's supposed to give a segmentation fault. If you try to write to a region that's read-only, it should give a protection exception, which is just reported as a segmentation fault in Linux. But if it's a read to a valid part, then it should just be a normal page fault, and the page table, the appropriate page should be brought into memory. So the trick is, in general, this linked list can get fairly large. And so you don't really want the thing to step through it. So they actually have a tree, I believe it's a splay tree, in fact, to also, so that given a particular address, a virtual address, it can fairly quickly identify which of these VM area structs is relevant for that particular address, or find that there is none, and so that should yield a segmentation fault. Okay, so let's do today's quiz. I think you'll find is an interesting one. Yeah. No.
You didn't call. You might have been Phil. I just need 5 minutes, to talk to students about the activities we do in EC, if that's okay.
Okay, they're taking a little.
It was scheduled, but maybe nobody told you. Sorry about this.
5 minutes?
If you want, we can come some other time.
Yeah, you can do it. Hey, folks. Those who don't know, this is Jelena Kovacevic.
Yep.
What's your name, right?
Perfect, yeah.
It's my Serbian ancestor.
No, it's great, yeah, exactly.
She's head of the ECE department, and she wants to talk briefly, so just put your little quizzes aside.
Oh, they have a quiz, I can...
No, please, just go ahead.
They're all happy to put the quiz aside,
Good.
sorry. And this is Barry Marchauer. She handles the student activities in EC. The reason why we're doing this, because every semester I have town hall meetings and student office hours, and some of you show up and tell me how you would like to have more social activities, more interaction with faculty outside of the academic environment, outside the classes and so on. And we do a lot of these already. So we thought we'd come and kind of sensitize everybody to it, and this is why Barry's here. Barry also sends weekly digests to all EC students on Monday mornings. So I suggest you look at it because she summarizes all kinds of things we do. And for CS students, I'm sure that CS does similar things, or if you see something you like in EC or you come visit us, we're happy to have you. So Barry, I'll just turn it over to you.
Great, thanks, Jelena.
Couple of minutes.
Hi everybody, I'm Barry. Like Jelena said, I do our student activities in ECE, and we have a couple of different things going on that I wanted to make sure that you're aware of. We have a De-Stress with ECE initiative. Every other week throughout the semester we have different things going on. Like for example, we have an ECE yoga class. Every semester we have, during finals and midterms, we have wellness spaces where there's crossword puzzles and granola bars and
Lots of free food.
Lots of free food, for sure. We also give out de-stress kits every semester. We have a movie night every semester, and we have a couple different wellness workshops. We actually have one coming up on founding happiness. So if you get my digest, check your digest and you'll see where to RSVP for that. And we also have faculty opportunities to interact with faculty that are informal and a lot of fun. So for example, a couple of our professors do game nights. Jelena has a puzzle night every semester, and actually she has one coming up in a couple of weeks. We have some professors who have taught our students how to play squash. We also have ECE faculty staff band. So if you play an instrument, we're having a jam session coming up in November. So
and actually, one of the 213 instructors from last semester, Franz from Ketty, is the main, jam band.
Yeah, leader.
Yeah, leader.
Yeah, Yeah, so it's a really interesting way to get to know your faculty in an informal setting. So we really encourage you to read your digests and keep your eyes open throughout the department for flyers and opportunities to de-stress and to have a life outside of class.
Okay, and apologies if you hear this more than once. We're doing a round of all our core classes, the sophomore level classes. So, you're welcome to fall asleep or continue doing your quiz if you have heard from us already. But this is just so you guys cannot say, oh, we want more of this, and we tell you we are doing it, so this is sort of a heads up. Thanks, Randy, and
Sure.
sorry for the interruption.
No problem.
Okay, continue doing your quiz. Bye, guys.
Thank you.
So I see that people aren't quite catching on to this problem, so let's work it out. So it says that it's a 32-bit address space, and that pages are 4096 bytes. So what's power of 2 is 4096? 12. So that will be our offset. And then there are 4-bit, 32-bit addresses, so how big is the page table entry? Well, page table entry will be, remember, it's got to have a physical page number and it's got to have some room for some flags. Also, it has to have the, so it will be 4 bytes. I guess you could maybe squeeze it into 3, but then that gets messy. So in a 32-bit system, just like in a 64-bit system, you saw a page table entry is 8 bytes. In a 32-bit system, it's 4 bytes. So that will be, so how many of those are in a page then? 4096 bytes, each is 4, is what? 1024, and so how many bits is that? To the, what's 1024? 10, right? So that tells you basically what you want to do is partition this into 2 10-bit chunks to get a 2-level translation system where, and that gets you your 32 bits. Does that make sense? So I know you just, in some ways, you just saw this for the first time on a different system and we're asking you to do it here. So it's not completely a question I'd expect you to jump right in and get, but that's the idea behind it. So the interesting thing is, I pulled those parameters off of a Raspberry Pi. So those of you who know, a Raspberry Pi costs $35 if you get the deluxe model. And it's the processor for it is what they call a system on a chip, and it's produced for cell phones, for smartphones. Not even high-end smartphones, more like a sort of low-level Android phone would use one of these, the chips they have in it. So that just gives you a sense of nowadays, even a fairly small device that you can buy for very cheap implements a virtual 32-bit system with virtual addressing, 2-level page tables. It supports a version of Linux and the whole thing. So nowadays, it used to be you only saw virtual addressing in fairly upper-end processors, but now that's sort of migrated down to some fairly low-level stuff. Okay, so that's, we'll finish off today then by looking at some of the Linux ways that implement the mapping of pages into memory, and how you can, as a user, actually have access to some of that. So the idea of the sort of relation between the pages that form your address space, and logically they're stored on the disk, say, typically, and the physical pages, the ones that happen to be resident in the memory at any given time, is that the virtual memory sort of maintains this correspondence between disk pages and physical pages by a process called memory mapping. And so a given part of the memory then can be backed up by a file, meaning it's a real file of the file system, for example, your executable program, or it can be backed up by an anonymous, or sometimes called a swapping file, which is one that as your program runs and it's filling up memory with whatever its data structures you're creating, those aren't really a standard file in the file system, but the Linux has to be able to swap those out somewhere if it needs to evict that particular page. And so it basically creates a region that's called the swapping region on the disk, where it's able to move pages back and forth. And these always come in when the first time they're touched and allocated, then the operating system will zero this out. And then if it's been written and the process is still running, it has to, if it evicts it, it has to actually write that file out to the disk. So one of the things we saw before was one of the great things about virtual memory is it allows the sharing of physical pages among different processes. And this is especially useful for read-only pages where they're, for example, code that you want to share across them. So that works by the same general idea that the one process sort of requests maps a particular disk file into its virtual address space, and that will then create, Linux will view this as a shared object then, and map it into physical memory. And now if a second process comes along and requests that same file be mapped into its address space, what it will do is create instead of making a second copy of it in the physical memory, it will just create pointers from both processes to this same part. So in other words, page table entries that are both mapping to the same page, but from different virtual addresses and different processes. And you'll see that actually the two don't even have to be the exact same virtual address, but they do have to be the same. All the addresses are sort of, everything's done in multiples of the page size. So the difference between any two virtual addresses between process 1 and process 2 will always be some, however many different the two pages are relative to each other. But the point is that now that this can run, this shared object can run, and the two programs can be accessing it. And you'll see, since the cache is based on physical addresses, even if these two processes are swapping it out back and forth, that cache entry will stay valid, and each side will be able to use it. One of the other clever things that they do in operating systems, including Linux, is use a trick called copy on write. And so that's the case where you want to have a block that is private, but it's also potentially writable. It's both readable and writable. So what the process will do, the operating system will do, is it will mark that block in each of these page table entries. It will mark it as read-only. But it will also keep track of the fact that this block is actually shared, and it will have a reference count for how many sharers there are of that block. And now if one of these processes comes along and tries to write it, what it will do is it will cause a, let me see if this is diagrammed. Yeah, so if one of these processes tries to write it, then the page table entry will say, no, you can't do that. And so that will cause a page fault. But now it will come up to the operating system, which can say, oh yeah, but this is a page I marked as copy on write. So what I'll do instead of aborting this and causing a fault is I will basically make a new copy, a second copy of this actual physical page, set up a pointer to that second copy by this process and let it write. And I'll decrement the reference count for this original block so that if there were, say, 10 sharers, now there'll only be 9 sharers. And so each of those is allowed to, through this copy on write trick, basically get their own private copy of this data if they keep writing it. And then once the final one is left, it has a reference count of 1, and so that's effectively becomes a private copy for it. So where this really comes into play is with our friend fork. Remember, the idea of fork is that it looks as if you have the child process, you've made a total copy of the entire address space for the parent, and only modified a few parts of it. But if you think about it, large parts of that two processes are likely to stay the same. The code, for example, will, and things like that, assuming I don't do an exec. So rather than sort of really making a copy, what it will do is keep the original copy, but use this copy on write trick to make it so that now I will only duplicate the pages that actually get updated by one process or another as it runs. So it's a pretty clever trick. Does that make sense to people? It sort of solves the mystery of how fork works. And now we've seen this a function you've experienced called exec. There's various flavors of exec. But the basic idea of it, if you think about it, is I'm trying to take a binary executable file and somehow pull it into memory and let that program start executing. So what happens is it uses this idea of memory mapping, that you map the the executable file into the memory space, and that will, and then tell the program to start executing it, will cause a whole bunch of page faults initially, as it touches new parts of the code or new data structures. But those pages then will just get brought in through this normal page faulting mechanism, and eventually your whole program will be loaded into memory and executed. So it does this by, as it does this, it has to initially create this linked list of VM area structs, but the actual pages itself don't need to be brought in until they're actually requested. One interesting thing I was just reading about is, so now we've seen there's sort of several different ways that the operating system can detect that two pages are, might be good candidates for sharing. We just saw it with fork. By default, everything is viewed as a candidate for sharing until it's not. When I've loaded the same binary file, so if everyone's running, if you have 10 different people running a Python interpreter, or a Bash interpreter, or a web browser, any sort of executable file that's pretty big and commonly used, well, the OS only needs to maintain one copy of that across the whole system. And similarly, if people are bringing in dynamically linking libraries, like the libc library or ones like that, again, those are files that get mapped into the memory. And so the operating system can basically share a copy there. So those are all cases where the copy is sort of known in advance who the potential sharers are. But I was just reading, there's an interesting feature they put into the Linux kernel about 10 years, almost 10 years ago, that's called kernel same page merging, where literally the OS is scanning through the memory, the physical memory, on a regular basis, looking for pages that are the same. And when it finds pages that are the same, it will then revert to just a single copy of that page and make it shared using the same copy on write mechanism. So you can think of it as, instead of sort of passively looking, using the sharing that's sort of built in, known in advance, it actually is actively looking for opportunities to share. And you think about the logistics of this, you have to be pretty careful. You don't want to just, you could waste a lot of time saying, oh, these look the same, oops, they're different, oh, they're the same. You know, that would be very inefficient. So you want to sort of not make this be too aggressive. And you might ask, well, does this really happen in real life? This sounds a little bit extreme. You know, why would my program happen to have the same data structures as your program at some given point? And it's not really for regular application programs this is useful. Where it happens is when a system is running what are called virtual machines. A virtual machine is a case where you can essentially run different operating system types on a single machine, single piece of hardware. And this is very commonly used, for example, in cloud data centers. A place like Amazon Web Services gives you a virtual machine that's your own, but it's hosting actually multiple virtual machines on a single physical machine. And so those are all examples of where there's a lot of common data because all the different instances of a particular, what's called the guest operating system, will have a lot of code and data structures that are common to each other. So this is there because, I mean, they implemented this because it actually is useful. And they've shown that for both Windows and Linux, in large servers, this kind of technique is worthwhile. So I thought it was interesting that the sharing is actually a real thing that's so real that they actually actively look for more opportunities. So you actually, as a user programmer, can make use of some of these same ideas by a function called mmap. And mmap is this general idea of mapping some region of memory from a file and creating a mapping between a file and a region of virtual memory. And that can be a read-only copy to bring in something into the memory system. It could be also be a writable copy that lets it actually transfer data back and forth between a file, say on a disk, and the memory space. So the idea of mmap then is that you give it a proposed starting address where you can just set to 0 if you're going to let the operating system figure out where in the virtual address space to stick it. How big is this region? And it doesn't have to be a multiple of the page size. And then various flags that set information about what's the protection on this, and what type of mapping is this? Is it a shared mapping, a private mapping, and so forth. You give the file descriptor for the file that you're trying to map, and an offset into that file. And basically that will create a correspondence then between some subrange of a file and some part of the virtual address space. So this example code is fairly small example of it, but what it's using, there's the pointer, is mmap, where I don't care what the starting address is, but I'm using it basically to take a file that I've read from some file that I've read in that is passed as the argument to this main function, and I'm going to print it on standard out. So I'm going to do that by mapping this buffer. Basically, I'm going to read the file from the file into a buffer, and then I'm going to write that buffer out. So the main thing this does is, you see there's no read. It only is writing, because it's relying on mmap to actually use the page faulting mechanism to read the contents of this file into memory, and then I can write that out. So that's mmap in one of its simplest forms. So why would you want to do this? Why would a normal application program ever use something like this? Well, it's a little bit faster if you're going to read an entire file's worth of stuff, rather than reading it with the regular read function. And the reason is, if you think about it, to read a file, what it has to do is first allocate the pages. It's going to hold the buffer that you're filling up, and that takes some time. And then you start reading off the disk, and basically what happens as you read is it copies it from the disk into a buffer managed by the operating system, and then the read then copies that over to the destination you've done. So by doing mmap, we avoid all of that. We basically just have it set up some virtual address space, and then ka-chunk, using the page faulting mechanism. It just brings us in page by page and fills up the buffer. You can use this also. You can map a region of memory that's, you can make it read-only, but you can also make it writable and shared. So potentially you can set up regions in the memory of two different processes that are shared, so that if you want to communicate back and forth or share some data, then you can, right? Because writes by one will be interpreted, will be seen as when the others do reads. The problem this has is, to do that in typical applications, you need various mechanisms to synchronize the two programs. And so you'd need some other way to manage this if you want to avoid total chaos. It also is a way that you can basically, if you have a large data structure stored on a file, in other words, a database of some type. So it's a sort of a long-term, long-lived collection of data, and you want to be able to yank it into memory, do some updates, push it back out, then mmap is the natural way to do that. Mmap will bring it in you update it, and then when you unmap that block, it'll all just be written back to the file. So it's not something that people use every day, typical programmers use every day, but for doing some very high performance memory I/O type of operations, it can be a useful idea. Okay, so this very brief pair of lectures we've done in virtual memory gives you some idea of it and some maybe appreciation for the complexity of it all too. That we see that it involves a combination of hardware and software. Things like the TLB has to be carefully integrated to the cache, and that requires, as soon as you have a TLB, there has to be some agreed upon standards for how big pages are, how big page table entries are, what their format is, and so forth. So Intel, or the processor company, defines certain attributes of the TLB. It also hardware has to support some type of exception handling so that you can have a page fault and reliably get back to where the program was executing. In fact, the early days of microprocessors were implemented by semiconductor companies who didn't know much about processor design, and they kind of screwed up the exception handling so that early microprocessors couldn't implement virtual memory. But over time, they hired some smart people from other computer companies and managed to straighten it out. And also, there's huge parts of the operating system. If you took a course like 410, you'd get into large parts of this. How do you actually manage all these tables? How do you implement page faults? How do you manage files? And all of that stuff is there's a lot of things there that we're only glossing over in this course. But you've also seen how then once you have this ability, how much sort of value it can provide to the program as far as handling some of the issues about memory protection, sharing of data between processes, how do you actually implement the initial execution, loading of a program into memory and execution, and things like that are all there handled through virtual memory. Any questions or comments? Okay, I think we're good for today then.